So I'm the team lead for the MySQL Optimizer team. So I'm going to go through the new optimizer that we've created. I'm going to start with an introduction to query processing in general. Then I'm going to talk a bit about why we are creating a new optimizer, or why we have created a new optimizer for MySQL. Then I'm going to go into detail on how it actually works. And then, so that you don't run off for the coffee break, I will save until the last minute to tell you how to actually start using it. So we'll end up with how you can start using the Hypergraph Optimizer today. So let's start with query processing. A client sends a query to a server that does some processing and sends back a result. The textbook version of how to do this is that you parse it, meaning that we check the SQL syntax, make sure that it's syntactically valid. Then we create a AST that we do resolving on. We look up all table names, column names, check that you have the privileges for that, figure out which data types these columns are in, and so on. And after that, we have a query that we know is semantically correct, that we can actually execute it. It makes sense to execute this. And after that, we do a rewrite of the query. Basically, if you have subqueries, we can change that into a semi-join or anti-join, or we can, if you say column equals 2 plus 2, we can change that to column equals 4. That's a value we can look up in an index. 2 plus 2 is not something we can look up in an index, that type of thing. So through this, we will get typically a more flat version of the query. You have a query with several subqueries. We will unnest those subqueries, ending up with hopefully just one level of a query. So that's when the optimizer kicks in. So the optimizer looks at one select at a time. So if you have subqueries, it will look at those subqueries individually. So if there are any subqueries left after the rewrite, they will be handled individually by the optimizer. And then in the end, the total query. So the optimizer is primarily tasked with finding the join order and the join methods for all the joins you have, and how to access each table. Are you doing table scan, index lookup, that type of thing? That's the core task of the optimizer. That gives us a physical plan, something that explains exactly how to execute the query. And a step we don't talk much about in MySQL is the code generation step, because we don't compile into machine code or any kind of bytecode or anything like that. We just generate a set of iterators that we iterate over. So MySQL is an interpretive execution model. So our query program is a set of iterators, a tree of iterators, and then we execute those. So this is like a textbook version of how it's done. Every database system groups this differently. MySQL has a parse step. We have a prepare step that does the resolve and rewrite that we really call transform in MySQL. We have an optimizer, one optimize step, and then code generation is just a thin layer on top of execution. So that's the MySQL model. And if we kind of clean this up and draw it in a way we typically do in MySQL, it looks something like this. Parse, prepare, and then since 9.0, a choice between two optimizers. And then execute. So if you're running with like a normal MySQL, now even before 9.0, when passing through the old optimizer, you will transform the plan from an old plan format to a new plan format before it's executed. That's the step we did before we open up for using the Hypergraph Optimizer. So the old plan format is less expressive than the new plan format. So the new plan format can express more types of plans than the old plan format. So we just transform it. It's a simple transformation from one format to another. So if you're running a normal query in InnoDB, you will pass through that left-hand line with the old optimizer. Same if you're using MySQL cluster running with NDB. But if you're using HeatWave, then you have for quite a while been using the Hypergraph Optimizer. We haven't talked much about it, but it's been there in the cloud. It's used in the cloud. And the hypergraph optimizer can optimize any type of query. The old optimizer can also optimize any type of query. So there's not much difference there in what they can do, but there's a big difference in what they can express in the end. So since 9.0, you can also switch optimizers. I will get back to that in the final slides. So this is what it looks like. In the cloud, you can get the hypergraph optimizer either for HeatWave or for InnoDB. Okay, so that's query processing. Let's look at why we decided to create this new hypergraph optimizer. The old optimizer has served us for 30 years now. It's served us well. It's amazingly good at kind of doing what it does. But it's showing signs of the age. So it's too simplistic. It's too much based on heuristics instead of cost models. It has an inefficient join ordering algorithm. It spends too much time calculating costs because it repeats the same calculations. It also has a bad failure mode. If it runs out of time and can't really check all valid possible join orderings, it will resort to a heuristic for producing the final plan that's really not good. So it will try for a while to produce all the possible plans for a certain number of tables, and then it will just give up and join in all the other tables in order of from the smallest to the largest. That's not a good failure mode. It only produces left deep plans, so it can only join in one more table at each level. It can't do join of table A and B, and then join of table C and D, and join those two join results together. That's not possible in that optimizer. It does not track interesting orders, so it doesn't track that if you have order by some column, it can actually read an index on that column and maintain that ordering through the entire query processing. It doesn't do that. It's an afterthought. It can check afterwards. Can it do a few tiny manipulations to maintain that ordering through the entire query processing and save an ordering step at the end, but it doesn't really plan for it throughout processing. It's not good at choosing between hash join and nested loop join. It's basically nested loop join focused, and then hash joins are an afterthought. And for us, it's not something you would see so much really, is that it's very tied to InnoDB and MyISAM and those engines, not so much suited for NDB or for the HeatWave column store, which have different execution models. NDB is much closer to InnoDB, so that's pretty okay, but HeatWave really presented a problem for this optimizer. So we set out to create a new one, and we have some design goals. We wanted to create a modern optimizer, but we also wanted something, we needed something we could trust, something that was kind of, to a large extent at least, tried and tested, because we can't do experimental development here. We have spent years creating this optimizer, and we need to be sure that there's something here that will work in the end. So we can't just go completely bleeding edge. Edge is fine, bleeding is not good. So we needed something modern, but something that we could also trust. It also had to be much more cost-based than the old optimizer. It had to take interesting orders into account, and it had to do cost-based join algorithm selection and cost-based everything basically. And we want these bushy query plans where you can take two join results and join them together. So not joining in one more table at each step. And for us, very, very important, one optimizer that solves the query optimization problem for all the storage engines that we have. So inode B row store and heatwave column store are very different. They have very different properties, very different execution characteristics, and we needed an optimizer that could really handle the differences here. I mean, an architecture where we could guide the search for the best query plan depending on which engine we are actually planning for. So the result was the MySQL hypergraph optimizer, and the name comes from the fact that we are using a hypergraph to represent the query. This is the same model we had earlier, just redrawn with more details. I'll get through all this in the next 15 minutes. But we start with parse, prepare, then we choose one optimizer or the other, and then we execute. And as you see the steps here in the hypergraph optimizer, is to construct a hypergraph. That's my next slide, how to do that. Then from that hypergraph, we are proposing a subplan, basically a plan for a small part of this query. And then we loop through this central loop here, proposing a subplan, computing costs, and updating best plans, until we have really examined all possible and valid plans. And as we do that, we maintain a list of the best plans we've seen so far. So the best plan for each sub-part of the query, and in the end we will have the best plan for the entire query. It just grows and grows to bigger and bigger plans. Then we do some final touches, and then we execute the whole thing. That's basically what it looks like. So the hypergraph optimizer obviously uses a hypergraph, and the names, well, we need a name, so we chose the name from the data structure we're using, and also based on the algorithm we're using. So a hypergraph is a generalization of a graph. And in query optimization, we use graphs to represent the dependencies between the tables in your query. So in this query, T1 left join with T2 joined with T3. We have two join conditions. We have the one between T1 and T2. T1A equals T2A. That's a line, the arrow there. It's an outer join, so we didn't know which was inner and which is outer, so we need the arrowhead. And then we have T2B equals T3B. That's the vertical line, and that is an inner join, so we don't really need to care about which is inner, which is outer, or which is on which side of the join. So the join graph for this connects T1 to T2 and T2 to T3. So based on this, you could say that, okay, we choose a pair of tables that are connected by a join, and then we try to join them together. That could lead to trying to join T1 with T2. But this is a left outer join. So basically, we need to know the join result of T2, T3 before we join in with T1. The join graph does not represent that. So basically what you would do is you have to do some hack around this, to do some filtering or something to figure out that, okay, this is not really a valid plan after all. So basically the dotted line between T1 and T3, that's a missing dependency in this graph. The hypergraph is different. Hypergraph is like a graph, but it's connecting a set of vertices to a set of other vertices. So in this case, the set of T1 is connected to the set of T2 and T3. This captures the outer join dependency. This captures the dependency that T2 and T3 are together on one side of this other join condition. So in this case, it's not possible to suggest T1 joined with T2 as the first step. So what the join hypergraph gives us is the theoretical guarantee that we will propose only valid join orderings, and we will also propose all valid join orderings. So we have theoretical guarantees here that we will produce all and only valid join orderings when we traverse this graph. With the join graph, we will probably propose all valid, but also some invalid join orderings that we need to filter out somehow. So based on this hypergraph, there's been research done to propose algorithms using this strategy. We based our work on an algorithm called DP-Hype, DP for dynamic programming and Hype for hypergraph. So we based our algorithm on that research and came up with our optimizer. So when we are proposing subplans for this, we are, as I said, taking one table first, look at all the ways to access that table. Then we look at another table, find all the ways to access that table, table scans, index scans, whatever. And then we see if there's a possible join between two tables. So yeah, in this case, if we looked at T2 and then T3, then yes, there's a possible join between those two tables. And then we try hash join, we try nested loop join, and we basically find all the different ways we can do this. So the idea is that we are building in a larger and larger and larger subgraph that eventually will cover the entire query. That way we build the query plan bottom up from a single table to all the tables in the query. So going back to this figure again, first step is construct a hypergraph. So one vertex for each table, one edge for each join condition, right? Or hyper edge if it's necessary. So from that hypergraph, we propose plans for smaller parts, starting with single tables and then joins after a while. So we start with table A here, for instance. We can do table scan of table A. So we propose table scan of table A, we compute cost, and here we feed in the cost model and statistics from InnoDB or from Heatwave or wherever. We compute the cost, and then we update the candidate best plans, meaning that we look at the list we have already. Currently it's empty, so we say that, okay, table scan of table A, that's the best plan for accessing table A. Then we go back to a hypergraph thing, table A, we can do index scan on table A. So we propose subplan, we compute the cost of that, and we update the candidate best plans. Table scan and index scan in InnoDB is very similar in cost because everything is an index. The cost is similar, but the index scan also provides an ordering. It provides the ordering of the indexed columns. So if that is relevant for a query, if you have an order by on a column that you have an index on, we will assign that interesting order as a property of this plan. So this plan has maybe a slightly higher cost than the table scan, but it also provides a small benefit in that it can provide an ordering that you will need later on for group by or order by or something like that. So then we say, okay, this is slightly more expensive, but it has another interesting property. So we keep that for now. Then we look at, go one more round around the loop. We don't have any more options for table A, but we look at table C. We do table scan on table C, compute the cost, update can best plans. Table scan on table C is the best thing we've seen so far, so we keep that. Then we'll look at let's say an index scan on table C. Subplan, compute cost, and we see that this is more expensive than reading, slightly more expensive than table scan on table C. And also, this ordering is not interesting. Like, it doesn't provide anything more. We're not going to sort on table C columns anyway. So, okay, we throw that away. We will never see that option again. Then we go back, we look at index lookup on table C. We can do that. So we compute the cost of that. Index lookup is very cheap. So when we look at our table of currently best options, we have table scan on table C, which is quite expensive. And then we have index lookup of table C, which is really cheap. But also it depends on actually having a value to look up. So it depends on table A already being in the subplan that we have. So that's also a property that we can use index lookup on table C if we know something about what to look up. So we have a property there on some condition we need in order to fulfill this. But it's very cheap. So we will definitely keep that plan, but since it's not an alternative to table scan, we will not throw out table scan. So then go back to our hypergraph, propose a new subplan. Let's say we've exhausted all the options for table C as well. We now try to join table A and C. We propose a subplan for hash join of table A and C. A as the build table, C as the probe table. Compute the cost of that. We update the list of best plans. We have no other plan for table A and C, so A hash join C is the best plan we've seen so far. We go back, we look at a normal nested loop join of A and C, compute the cost of that, compare to the plans we already have, and a nested loop join is much more expensive than the hash join in this case, so we already have the hash join, so we throw out the nested loop join. Go back, propose a subplan. This time it's a nested loop join with an index lookup on C. Compute the cost, look at the best plans, and we see that a nested loop join with index is much cheaper than the hash join, which will actually have to do the table scan on table C. The index nested loop join will only do the index lookup. So suddenly we can use that special index-based lookup on C that was not a generic solution, but you can use it for the nested loop join with index. So we throw out the hash join, say that's not a good option anymore, and we keep the nested loop join with index lookup. And so we loop through this and then grow steadily larger and larger and larger subplans until we cover the whole thing. And at the end, we will have the best plan for the entire query, bottom up. So we had all these dimensions, as I said. The total cost is 1, definitely. Also, let's say you have a materialized table. The cost of materializing that table is high. The cost of rereading is very low. So we have initialization and rescan cost to represent those two different things. If you loop over something several times and rescan cost is low, that's a good option. If the rescan cost is really high, looping over it is very expensive. And number 4 here, the dependency on the tables, that's what I said about, let's say, an index lookup on table C. It depends on table A. If you're comparing a column in table A with a column in table C, then it depends on that column in table A actually being present in the subplan you're joining C into. Ordering, as I said, if it's necessary or useful for order by or group by, we will keep that as one dimension. We only care about the orderings that are actually being used in the query. We don't keep all orderings. Then we check also a dimension on whether we can do sort by row ID for this thing. If we do sort by row ID, it means that our sort buffer only contains the columns you're sorting on and the row ID of the row, meaning that we will fit a lot of rows into the sort buffer. That's as opposed to taking all the columns of the table into the sort buffer, all columns of the query into the sort buffer, and fitting fewer rows in the sort buffer. So that could also be a benefit. And the last one is for update and delete. If a query plan can be executed and actually do the updates and deletes while we are reading from the tables, then that's a very efficient way of doing things. But it means that the update and delete can't affect the results of the query we're currently processing. So that's also a property that some plans have and some plans don't. And we keep all the plans that are better in some way than the other plans. So lower cost is a no-brainer, but also maybe a higher cost, but it maintains a sorted order. Or even, as we said, and even lower costs for index lookup on table C was a really good option, but it had a dependency on having a value to look up in that index. So it wouldn't replace a table scan. So those are the 7 dimensions that we have currently. We may add more. I don't think we will remove any, but currently we have 7. We are able to extend this as we see fit. So basically the optimizer will go through this loop over and over and over again until it's done, until it's built the whole thing. It's a bottom-up planner, so we don't have a query plan until we're actually done with the whole thing. So how many times we have to go through this loop depends on the number of tables, the number of join conditions, the number of indexes you have, all that stuff. This could be like, for a lot of queries, this is fine. We can do the full search, but in some cases, this will take too long. We can't keep optimizing forever. So we have a rule for going back to heuristics if our query is just so big that we can't spend all that time optimizing it. So as I said, we have this hypergraph that encodes basically join ordering. The hyperedge between T1 and T2 and T3 said that T2, T3 had to be joined together first, and then we could join with T1. We can use that trick to encode into the hypergraph artificial hyperedges that locks join ordering. So we can use that to reduce the number of join orderings that are possible to generate from this hypergraph, meaning that the optimizer will run for a shorter amount of time. And what we can do is that we can use this heuristic to find the most obvious join orderings. The single most obvious join ordering here that we can lock in, we will say that, okay, this one we will force to be done first. And then we can do that with more. We try to do that with as few as we can. So we basically bisect to find the fewest number of artificial hyperedges we need to add. And that brings us down to below the memory budget, the time budget. So looking at this graph again, if we go around this enough times, basically we have a counter for how many times we loop through this proposal loop. If we exceed some count, we will, instead of updating the list of plans, we'll diverge back to the hypergraph, add artificial edges as few as possible, but the most obvious ones, the most obvious join orderings will be locked in, and then we go back and we are guaranteed that we will complete this loop within our time budget. The good thing about this is that even though we're going back to heuristics, as we said, the old optimizer has a bad habit of doing that when it runs out of time. We have to go back to heuristics here as well, but we can use heuristics on the easy choices. We do the easiest choices first on heuristics, and then basically the optimizer runs the full exhaustive search on all the difficult choices. So we're able to not just give up on time, but we go back and make the easy choices using simple rules and use actual cost models on the actual tough rules. Okay, so at the end, how can you start using this? There's a trick here with the hypergraph optimizer equals off and optimizer equals on. That's an optimizer switch. So if you do set the optimizer switch hypergraph optimizer to on, then you're using the hypergraph optimizer. It's as easy as that. And since 9.0, you could do that in the cloud. You can't do this on-prem or in the community edition at the moment. We haven't enabled that. But in the cloud, since 9.0, you can do that. You can also set it globally for your entire instance if you want to run all your queries with that optimizer. But if you want to test it, just do that. And as I said, if you've been using HeatWave, actually since 8.031, you have been using this optimizer. You just don't know it. It's been there, and it's been giving us amazing results in HeatWave. And we are hoping to get really good results for InnoB as well. I don't have any numbers to share with you. We're seeing really good numbers, but we're still working on tuning the cost model to make it even better. So the really good thing about this is that we have just started on the benefits of switching the optimizer. So we have the new optimizer, but the cost model is really what will drive all the new stuff that we get from this. So we have so much more to gain in the years to come. So now we have a new architecture that will really bring us forward for many years to come. That was it. Thank you.